I'll begin. Heavenly Father, we thank you for the rain, and I thank you for these students. Just help us to understand a little bit more about partial differentiation today. We thank you, Lord, for being the awesome God that you are, that you love us each and every day, whether we love you or not. We thank you that you're awesome, and that you came to earth and died for us to forgive us our sin if we just accept you into our heart. We thank you that if we do that, we have your righteousness, not our righteousness, Lord. In your name we pray. Amen. All right, so I'm going to talk about the gradient vector field. And the concept of a contour plot. Now, that's the big topic for today. But before I do that, I do owe you, and it seems especially relevant given the general patterns I've seen amongst the student body recently. I need to give you some sick examples. Pathological. And so there's two main pathological examples. These are the things that won't happen to us today mostly. But here's one. If you have a function that's like almost everywhere 0, right? So this actually doesn't really fall under the header. But I need to remind myself, I need to show you this. So suppose you have a function that's almost everywhere 0, except it's 1 on the coordinate axes, right? So let's suppose f of x comma y is equal to 1 for x, y equals to 0. Well, for x equals to 0 or for y is equal to 0, right? In other words, on the coordinate axes, it's 1. If this is the case, you can calculate partial derivatives, right? What would partial f partial x be at the point 0, at the origin? 0, right, yeah, because, and they would exist because the functions are just constant along those lines. So if you composed f with the coordinate axis paths, you just get the constant function 1, and of course you differentiate that, you get 0. So yeah, the partial derivatives are 0. How about the directional derivative in any other direction except for the coordinate axes? Any other direction. If you think about any other path. What's that? Right, yeah, it's not continuous, so it's certainly not differentiable, right? If I think about any other path, like this one, right, I get to here, it jumps. It jumps right there, right? So you can see that the directional derivative u hat f at the point 0, 0 does not exist unless what? U hat is equal to plus or minus x hat or plus or minus y hat. So the partial derivatives existing does not tell you anything about directional derivatives in other directions in general. There are sick examples like this. You're like, well, that's just because the function's not continuous, right? That's a problem because the function's not continuous. Surely if the function's continuous, it'll be okay, right? Well, I'm sorry, but even that won't do it. Here's an even sicker example. So suppose you have a function that's, z. So here's the graph, f of x comma y is equal to 0 for x, y. Let's say for y not equal to x squared. All right? But then I say along the curve y equals x squared in the domain, the function f of x comma y is just equal to x squared for y equals to x squared. And so it's a funny function. It's 0 almost everywhere except for this one curve, this one parabola where I'm telling you it goes like x squared. So the graph of that is really weird. It's got this one kind of hair sticking out of the graph, something like this. I don't even know how to graph it very well, but it's got this one errant piece of the graph, and then that's of course missing down here, right? So here's this piece of it. So if you look at the function, you do have f of x comma y going to 0 as xy goes to 0. All right? It's continuous. at the origin. F of, the limit as x comma y goes to 0. In fact, you can rigorously prove that the limit of the function is 0, which is the value of the function at the origin. It's continuous. And how about directional derivatives? You can also show this rigorously. You can show the directional derivative of this function in the u hat direction at the origin, no matter what u hat is. Right? No matter what u hat is, even this one hair that's kind of sticking out here, if you will, it doesn't matter. It's got a horizontal tangent, right? It has slope 0 even if you look at that piece of it. In short, all the directional derivatives are what? 0, yeah. But this is an example of a function which has all directional derivatives existing being 0, and yet I wouldn't say that this function is what is called differentiable. If a function is differentiable, it means that there's something like a tangent plane that well approximates the function close to the point of tangency. And a tangent plane just does not take into account this errant hair that's sticking out there, right? It's odd. And so the thing that unites both of these examples is they lack what's called continuous differentiability. Continuous differentiability, we say f is continuously differentiable if what? At some point, let's say p, if the partial derivative functions are continuous at p, near p, on an open set containing p, to be more careful. Both of these examples fail to meet that criteria. If you have continuous differentiability, then we'll see as we study on that, in fact, the function's well approximated by some tangent plane close to that point of tangency. All right. Sorry, I should have said this last week, but look, now I've cluttered this otherwise pleasant lecture. Can I erase this and move on? This is a somewhat technical point I'm making to you right now. Some people would argue it doesn't belong in Calculus 3. Those people might be right. They might be right. I don't know. What is Calculus 3? Who's it for? I'm going to erase. All right. Now let's get back to the main course for today. So we're going to look at functions of two variables primarily. All right. So consider, not this one. So our function, something like a function of two variables, x and y, right? And the gradient of f, what do we say? Nabla f, what was it? Was partial f partial x, partial f partial y, right? It's the so-called gradient of f. So what I want to understand today is, what does this mean geometrically? What can we do with it geometrically as we study functions of two variables, right? So what is this really? So what we really have is we can take the point P in the domain of f, all right, and attach the gradient of f at the point P at P. In other words, if we think about this nabla f correctly, it's not just something we can do to the function. It gives us a way of assigning a vector at each point in the domain of f. So actually, the proper view of this thing is, another way of saying it is this is a vector field. What's a vector field? A vector field on an object is some way of assigning a vector to each point on the object, just one vector. You could talk about a vector field along a curve. You could talk about a vector field in a plane. You could talk about a vector field along a surface. You could talk about a vector field through a volume. These are all different things you could assign vector fields to, right? Again, attach a vector at each point. This is a vector field. Do you have a question? Okay. So let's look at an example. Let's see here. How about f of x comma y equals to x squared plus y squared? This is probably my favorite example for this. What's the gradient look like? Two x, 2y, right? Now, if I'm so foolish as to try to plot this by hand, let's do it. So, all right, what's this look like? Now, when we're studying a function of two variables, a useful way to understand what's going on with it geometrically is to look at its so-called contours, right? The contours of a function of two variables is what? Here's a definition for you. Given function of two variables, let's say fxy, the kth contour is the level curve f of x comma y equals 2k. So a contour of a function of two variables is a curve in its domain. Now, I will explain shortly how these correspond to very particular features in the graph of the function, but the contour itself is in the domain. It's two-dimensional at the moment. Whoa. Wow, that was something. Okay, so how about the contour of level minus 1? What is it? I already drew it. I already drew the level minus 1 contour. Why? Yeah, there is none. You look at x squared plus y squared equal to minus 1. No solution. Where's the start to be a solution? 0, right? And then how about level 1? Level 2? That's not quite right. Level 3? Anyway, you get the idea. So these are the contours of f of x comma y equal to x squared plus y squared, right? Which are what? AKA circles. So what's the deal with the gradient vector? What does the gradient vector have to do with these contours? Let's picture them. So let's pick some points. Let's look at the I'm gonna say that, so I said this one was the unit circle, right? The middle one, the inside one. So if this point is 0, 1, I take the gradient of f, I plug in the point 0, 1, listen to me, 1, 0. What do I get? 2, 0. If I take the gradient of f and I plug in the point 0, 1, what do I get? I get 0, 2. Right? So plot those, attach those to the point in question. Something like this, right? 0, 1 up here, it points straight up, right? What happens when you look at the gradient of f, plug in the point minus 1, 0, what do you get? You get minus 2, it points this way, right? And you can keep going around, right? You can keep plugging in points. What do you get? So can you tell me what's going on with this gradient vector field? It's what? It's centripetal? Yeah, it's kind of like it's along the radial lines. Right, there's a vector in every direction. I'll also agree with that. Now, this is the level 1 curve, right? Maybe this one out here would be the level 4 curve. I don't know. I'm not being scale careful. My point is, as you go out from the origin, what your levels are doing what? They're getting bigger, right? Larger and larger. So the gradient vector field, if you look at how it behaves on the unit circle, it's pointing in the direction you must go to level up. Right? If you want to get to higher contours, just go in the direction of the gradient vector field. It points in the direction, as we talked about last class, in which the function is increasing at the maximum rate, right? Remember, what's the significance of the gradient vector? The magnitude of the gradient vector at the point P is equal to the maximum rate of increase, right? So if we take the directional derivative in the direction of the gradient vector, we get the magnitude of the gradient vector at that point as the rate of change, right? So if you can make a picture, right, and you at each point in the picture, you draw a little arrow which points in the direction in which the gradient is pointing, what does it tell you? At each point, it tells you which direction you should go in order to get to the higher level curves. Yeah, it tells you exactly. It's like a compass that always leads you uphill, is what Dr. Kester used to say. So if you followed the compass, it'd be very tiring, and you'd always end up on top of a mountain, right? What's that? Leading to another. Well, what if it's the tallest mountain? I think you'd just be stuck. You wouldn't know what to do, right? And that's kind of what happens at the origin here. Which way should you go to level up? I don't know. Gradient 0 there. That's called a stable point, or a critical point for the function. A point where both of the partial derivatives are 0 is a point where the gradient doesn't really tell you which way to go to get bigger. If you want to get smaller as fast as you can, what do?
You run from the stable point.
Right, you go the opposite way. Well, you go the opposite way, right? You go in the opposite direction to the gradient vector field. Now, I just drew you a sample selection of like what, 6 or 7, 8, I don't know how many, I can't count. 1, 2, 3, 4, 5, 6, 7, 8, 8, I guess, right? I mean, why did I draw those 8 and not more? It's just my choice. I mean, if you're going to try to plot a vector field, how many different vectors do you have to plot? I mean, if we're talking about a vector field in the plane, there are infinitely many vectors we're attaching, right? So these pictures I'm drawing, they're just a representative selection of the vectors that form the gradient vector field, right? Let me show you some better pictures that I can't hope to produce by hand. But before I do that, let me just make a connection. Let me draw the contour plots here. One more connection, then I'll get out the projector. One more. What's the connection of these contours with the graph? What's the graph of the function look like? Let's talk about that before I forget. What's the connection to the graph of the function? Here's what I think. I think about drawing the domain of the function, right? And I think about laying down the contours in the domain, viewing the domain as the xy plane, right? You can envision the contours just kind of sitting there. There's the 0 contour, here's the 1, here's the 2. I'll just try to draw 3. So there's the circles in the xy plane, which correspond to, let's say what? You know, k equals to 0, k equals to 1. Let's say k equals to, let's say k equals to 4, k equals to 9. Because, you know, 1 gets me circle radius 1, right? 4 gets me a circle of radius 2. 9 gets me a circle of radius 3, right? It's not linear. And so if you just think about taking these circles and then lifting them to these corresponding, you know, to the corresponding levels, right? So the origin just sits there. The circle of radius 1, you think about kind of like lifting it up to here. think, lift it 1 unit up, and then think about lifting this one 2 units up. And then think about lifting, sorry, let's say 2, I meant 4. My picture's not quite right, obviously. I'm just doing my best that I can by hand. 9 units up. So you think, and as you lift these contours up, you form the graph. Kind of like a toy maybe you had, I don't know. Looking for something. Yeah. Kind of like one of those eyeglasses or whatever that collapses down. Trying. I was trying. I attempted it. It didn't quite work. Fine. Let me fix this. This is sad. I hope you get the idea. In your textbook, there are nicer pictures, right, where you have a picture of a graph, right, and then below it you can picture the contours, and then each one of the contours will give you like a particular trace on the graph, where that whole trace is at a particular z-value. So what's awesome about this connection here is simply this. Two dimensions we can understand pretty carefully, right? Most of us have a relatively reasonable grasp of two-dimensional coordinate geometry. It's also true that most of us are pretty bad at drawing these things. Well, great news. If you use contours, you don't need to, because you can study the geometry of this graph by studying the corresponding geometry of a family of contours on the graph, right? Now, you have to understand what you're doing, otherwise it's just kind of a meaningless exercise. But with that understanding, if I draw something like and I say that this is level 1, level 2, level 3, and here's level 2 again, and then here's -10. I could draw something like that. It would mean that would correspond to a graph of a function of 2 variables, right, in 3 dimensions, and yet there's no earthly way I could hope to draw the 3-dimensional graph by hand. But I just made that up, and I think most of you, if you follow what I just drew, can kind of understand. You can tell me some things about this thing I just made up all of a sudden already, right? There's some kind of like pit in here, right? It's diving down, and whereas here is like the top of a mountain, right? Where would you forecast the gradient vector would be 0? Yeah, there's probably a place inside here where there's probably a critical point in here, and there's got to be a critical point somewhere in there. There's got to be probably a place where the gradient is either not defined or 0 in those 2 regions. And if I was to ask you to draw the gradient vector field, you could do it. Well, you could try. And you notice I'm drawing the gradient vector field. What's the formula for the function? Yeah, z equals, it's f of xy. That's about the extent of it, right? I didn't give you a formula, is the point. But it doesn't matter because these are basic, these are I'm telling you something geometric about the function. You don't need a formula to understand which direction the gradient vector field's going in. It just points away from the level curve perpendicular to it, right? Remember what we proved last time? In what direction, with respect to the gradient vector field, what direction do you go to stay constant? Or let me put it in different terms for today, to stay on the same level curve. You go perpendicular to the gradient vector, which would be parallel to the curve. Yeah, that's a dangerous. Whenever you guys say parallel or perpendicular, there's always the chance that I'm going to disagree with you because I think you're talking about the wrong thing. But it's not your fault. It's just there's 2 things to talk about here: the level curves and then the lines which kind of line up with the gradient, right? Okay, so there's other things we can do here. Remember I talked to you guys about theta hat and r hat? We've been using y hat and x hat, right? What are those? Unit vectors, right? if you had to say what x hat and y hat did in terms of a function of two variables and increasing and decreasing, how would you describe what x hat is? I mean, think about this. X hat, what does it do? Let's think about it for a second here. This points in the direction of what? Increasing x values, right? Yeah. So if I have f of x comma y equals to x, what happens when I calculate the gradient of f? 1, 0. What is that? X hat. See? The gradient points in the direction of increasing x, just like x hat. What about r hat? How about f of xy equals the square root of x squared plus y squared, right? That's r, right? A short calculation shows you that the gradient of f there is actually x over the square root of x squared plus y squared, comma y over the square root of x squared plus y squared. There's a partial differentiation I should work out there. I'm just not doing it because I don't want you to lose track of my point. That vector points in the direction of increasing radius. I'll give you a second to work that out while I'm getting my computer to behave.
By default, that would didn't point away from the origin.
Indeed. Yeah, it would point away from the origin, that's true. So the idea I'm trying to get you guys to see is if I want a vector field which points in the function in the direction in which something is increasing, right? I just take the gradient of that thing I'm interested in, and that will give me a vector which points in the direction in which that's increasing at the point in question. And that's exactly what we want for r hat. It's the unit vector which points in the direction of increasing polar radius, right? Do you guys see how to calculate that? I just glossed over a differentiation, which isn't altogether trivial. Let me work it out. Oh, but you should see that this is what? Before I get back to this calculation, r hat is, what is this? X over r is cosine theta. And this is sine theta. That's the formula we gave for r hat later. I argued by geometry that's what it had to be. Now I'm telling you we've derived it by calculating the gradient of the formula square root of x squared plus y squared, which is equal to r. Fine, let me do that. Partial x of r is what? We get what? 1 over 2 times the square root of x squared plus y squared, right? And then I have to do the derivative of the inside function by the chain rule, right? But what's that? Yeah, that's 2x. So I get 2x over 2 times the square root of x squared plus y squared, which of course is just x over r again. In other words, partial x partial r is really cosine theta. Likewise, partial r partial y is equal to y over r by almost the same calculation, and that's sine theta. Using polar coordinates, of course. All right, so let me just take a breath. Are there questions so far?
How do we determine the level 1, level 2, and 3, like looking at this graph? Because
They were given, so it's like a topographical map.
Yeah.
On the topographical map, they have to put down the levels.
Right.
It's given.
It's given. Okay.
Yeah. There are some rules, right? Like different levels can't intersect.
Right. That way.
Here's a better picture of the first one I did. Let me kill the lights in the front. So you see here's the x squared plus y squared. And I think I use Maple to make these. It doesn't matter. You can use anything. Dr. Wang, I think, has gotten this to work in Mathematica now, whatever. And you can't read too much into the length of the arrows in the generic computer algebra software. They don't usually plot the length of the gradient, the vector field to scale. So usually the only thing you can really get from these plots is the direction of the vector field, not so much the magnitude at a given point. There is some indication of magnitude here. You see it's smaller at the origin and it's larger as you get further out, which is accurate for the x squared plus y squared function, right? Here's the x squared minus y squared. What would that be? Z equals x squared minus y squared is a hyperboloid, right? Oh, goodness gracious. Get back here. Ah, stop that. Stupid. Sorry, I need to go to like Adobe counseling or something. I don't know. My inability to scroll. It's always vexing. Yes, I would like to scroll, please. Could I have scroll? I enabled scrolling earlier today and didn't remember. Curses upon you, Adobe Acrobat. Okay, sorry. I will stop cursing the software. So what you're looking at here is a picture of the contours of x squared minus y squared, right? So you said x squared minus y squared equal to 1, you get a hyperbola. You said x squared minus y squared equal to minus 1, you get a different kind of hyperbola. One opens up, one opens sideways, right? But you get a family of these things, and as you lift these levels or sink them down above or below the x and y plane, they would form that graph that we saw before of the hyperbolic paraboloid. And then superimposed here is the gradient vector field, which, as you can see, always points in the direction to level up, right? So level up, level up. So let's see here. I think these are the positive contours. These ones. These are the negative contours. Yeah. So it's probably like level -1. There's asymptotes. The 0. If you look at x squared minus y squared equal to 0, you get the lines y is equal to plus or minus x, right? Those give you. Well, they're not plotted here, but any questions? Yep. It's very much related to a slope field, yes. The difference is, I guess, with the slope field is what's the point of the slope field? You're graphing, yeah, the slopes of like dy dx, right? So here we're plotting the gradient of a function of two variables. I think I have more to say about your question on another day. So it's not a bad question. I will analyze at some point the problem of exact differential equations, and there we'll actually identify the vector field with the slope field in a systematic way. But as tempting as it is for me to dive into your question or comment or observation, I should not. Here's a picture of the stupid one I just put on the board, right? Like this one, I can do a pretty good job of graphing any given day. This is the vector field x hat. It's very boring. It's always x hat, x hat, x hat, x hat. It's constant, right? And as you can see, it does point in the direction of increasing x levels, right? As you travel right, you go up and up and up in the x. Likewise for y hat. Here's a picture of the y contours, as well as the corresponding y hat, right? Again, kind of boring, but I think it's a good example to understand what's going on geometrically with the gradient and the contours, right? What's the graph look like here, by the way? If you looked at z equals to x or z equals to y, yeah, it's a very boring plane, right? Through the origin. So. Now, my point to you is the more interesting aspect of this is that it shows us actually a method to calculate the unit vectors in the, if you have a pair of coordinates, right? If I have a coordinate system on the plane, say f1 and f2, so like f1 equal to a constant or f2 equal to a constant would give you the f1 coordinate curve or the f2 coordinate curves, right? Like if I set x equal to a constant, as y varies, it's like a y coordinate curve, right? Y is varying, x is held fixed, or vice versa for x. And if I hold y equal to constant, x varies, so I have like an x coordinate curve. Well, suppose I have a more general thing like f1 and f2. For example, r and theta. Well, I can calculate unit vectors in the direction of increasing f1 or increasing f2 by just taking the gradient. But then here's the wrinkle. The gradient vector might not be unit length, right? So I have to rescale it. But once I do that, I have a unit vector in the direction of increasing coordinate, whatever coordinate system you like. And so here it is. As I was just calculating, the gradient of r ends up being x over r, y over r. But with polar coordinates, we get back to r hat that I motivated geometrically earlier this semester, right? How about, bless you, how about the theta? Well, theta's kind of a pain, but because you got to differentiate inverse tangent, but it's not too bad. That's 1 over the thing plus 1 over 1 plus the quantity inside the inverse tangent squared times the derivative of the inside function. You do that calculation, it works out to this and that. You notice that there's a big difference between the way x appears here and the y appears here, so the partial derivatives work out a little differently. The minus is coming because x is reciprocal, so you have like that minus 1 power, so when you do the chain rule on the inverse tangent, you pick up a minus here that you don't get over here when you do the y derivative. Anyway, what is this? Well, this is like a minus sine over r. This is cosine over r when you put it back in polar coordinates, right? Not a unit vector. In fact, this vector has length what? Well, you can factor out a 1 over r here, right? This is clearly a unit vector, sine, cosine. This is a unit vector. So you've got this extra scale factor out here, which is not desirable. So to get theta hat, just wipe that out. And that's what we wrote for theta hat earlier. As you can see, though, it's just the unit vector that points in the direction of increasing theta. Here's a picture. These are the contours of the r function, circles. And here's the r hat, which is always length 1, but as you can see, always pointing outward, radially outward. And here's a foolish attempt at a picture. This isn't my fault. This is the graphing software. As you can see, it chokes on the plus or minus pi over 2. Inverse tangent doesn't do well there, huh? But that said, you can see how they wrap cylindrically around. They're always pointing in the direction of increasing standard angle, right? So this is the important thing that we must take away from everything we're doing today. The gradient vector field, nabla f, is perpendicular to the level curve. That is at the heart of everything I've told you, all right? So you're like, well, who cares? Can you give me a real world example? Indeed, I can. Here's a good example. If you have V of xy, that represents the voltage due to a point charge at the origin. So 1 over r up to some units. The electric field, it turns out, is actually minus the gradient of the voltage. Now there's a pesky extra minus in there we have to put for physical reasons so that energy is conserved, and that energy is potential energy plus kinetic energy rather than something weirder. So there's a pesky minus there slightly clouding the issues, but see, with the electric field, it points in the direction of what? Since there's a minus there. Does it point in the direction of increasing voltage lines or decreasing, right? Because of the minus. But otherwise, the story is the same. So the equal voltage lines, the gradient to the voltage minus that is the electric field. So the electric field points perpendicular to the voltage lines. It's an example from the world of real Hey, I'll shut up. Let's see here. What else? Here's another example. If you have an ellipse. I want to show you more pictures, so let me stop with these non-picture examples. I can write these out. Here's a good one. Suppose we have a level curve, f of xy equals a k, right? So xy equals to k. If you look at different contours, you get these things, which is kind of like the one we were looking at before, but it's been rotated by 45 degrees. The one I had up a little bit before about x squared minus y squared was the same picture essentially, but rotated 45 degrees. But here's some pictures of the gradient vector field again, and here's a picture of the. Let's see, what am I looking at? I have z. Oh, I'm looking at two things actually. I'm also looking at the z equals x squared y squared example, which is different, right? So what did I do? Which one is which? So this is the contour plot for x squared y squared. This is the contour plot for xy, right? And here I've graphed both the which one is which? The x squared, the z equals x squared y squared is the red, which has these contours. The blue is the z equals xy, which is, as you can see, it's growing slower, right? And it bends up along these directions, right? Whereas it bends down on these two sides, right? You see it's going up, leveling up, which means that the contours are going down if you go that way. Contours are going down if you go that way. As you can see, the leaves pull down here. On the other hand, this thing, x squared y squared, it just goes up, right? Z equals x squared y squared. As x and y get large, z gets larger. So the contours are they're always positive and they're always increasing as you go away from the origin. As you can see, that's the picture of the graph as well. So the point of these examples is just to try to showcase the connection for you between the graph, the contours, and the gradient, right? These things go together. They're part of a larger story. I hope you're starting to see it, at least. Obviously, some of these things I have no hope of graphing by hand, right? So, yeah, more examples, right? These are nice, though. Here's yet another thing that we started with today. Yeah, see, these are the contours, right? And the color coding. You see the color coding? So this is the red contour is red, and then as you go up, you get further up, you go to the blue contours and the blue part of the graph. That's how to look at that. These are created with maple. Here's the corresponding. But you see, I don't know about you, but man, I can get a lot more from this than that. Yeah. Yes, I will take that. Here's a fun one. Here's what are we looking at here? We're looking at z equals cosine of x. Right? This is actually what's known as a cylinder. You're like, what? Yeah, this is a cylinder. A cylinder, if you only take any curve and you just repeat it over and over and over in another direction, is a cylinder. You're most familiar with right circular cylinders, right? But technically speaking, this is also a cylinder in the mathematical sense of the term. Anyway, there you go. There's the contours. And see if I have more show and tell for you. Ooh, look at this. Cosine of xy. Oh, see, that's weird, right? Because if you think about x, you're feeding it the value of what is it? What is z equals xy? What is it? Is it the hyperboloid? What is it? It's something weird. So if you think about xy, what's it? It's positive in quadrant 1. It's positive in quadrant 3. It's negative in quadrant 2 and quadrant 4. And it's just generally an unpleasant quantity, right? And then you're feeding it into cosine, which is periodic. Right? That's weird. And so what's happening, of course, as you get further and further out, x and y is changing faster and faster, which means you're going to go through cycles of cosine. faster and faster, and the waves get more and more densely packed the further you go out. It's quite awful. And so there's a picture. This is also an example of where computer algebra software is only as good as the resolution size, right? This is not an actual feature of the graph, right? What you're looking at here is an artifact of a failure to take enough sample size, right? You've not taken a sufficiently large data set in order to plot this thing. That's not a real thing in the graph. Now here's the kind I might ask you to write on the test. See? This I think you can do by hand. Fair? Oh, now you're taking a picture. It's funny. And that brings us to 3D. But we'll do that tomorrow. So, thanks, guys.
Everyone needs to buy 3D glasses first.
You got to get 3D glasses?